Okay, so we have some people still joining, but we'll start, and I'm sure they can pick up wherever we're at. Start with a short introduction. My name's Adam Bond. I'm Business Development Manager for Xylem Water Solutions UK Limited. My main area of the business is wastewater treatment, predominantly secondary biological treatment, looking after the sanitaire, aeration and blowers and flight mixer product brands. I'm joined this afternoon with Magnus Spens. I'll let Magnus just give a short introduction to himself.
So my name is Magnus Spens. I'm a global product manager for blowers, mechanical aerations and bio treatment systems. And that doesn't mean the biological systems we have in our portfolio. It's rather tying products together in an efficient way, and this is some part we will cover in this webinar and what the potentials are there. I'm sitting in Sweden, so you see the northern light in the background as symbolic for that. But actually, we have nice weather here, no northern light at this time of year.
Okay, so thanks for joining, everyone. So this afternoon, we'd just like to talk to you all about wastewater treatment, and predominantly looking at how, using design and control of systems, we can increase performance, gain efficiencies, and drive better process performance from the equipment that goes into those plants. We'll cover a little bit first on an introduction to wastewater processes and plants, and then move on to the secondary wastewater treatment process, the biological treatment process, different ways in which you can design and take advantages of systems, and then looking at control optimization and smart performance using data through the system. So I'm sure we all know why we need waste to treat wastewater. Obviously, initially and most importantly, it's protect nature, protect ourselves, to protect our health, and to protect the health of plants and other living things within our ecosystem. So that's returning water back into the system with low oxygen levels, low BOD growth, and a good amount of eutrophication. It's all about, as we say, protecting beaches, protecting water sources, so we can enjoy them and make use of them for further use for clean water. So in a typical wastewater treatment works, we have various stages. We have head of the works, so we're removing large particles, sand, fibre, grit, rag, all sorts of things that we don't want going through the treatment works and causing disruption to the mechanical equipment. So we're using things like screens, grit chambers, and other technologies to remove those large, heavy particles. We then move through to primary treatment. So that's another stage of removing organic particles, so removing slightly smaller elements, and we do get some treatment within the primary treatment step. Following primary treatment, we move to secondary treatment. So in secondary treatment, we're using technologies such as aeration lanes, ASPs, oxidation ditches, sequencing batch reactors, and other processes. And we're using things like aeration to remove organic matter, BOD. We're also removing chemicals, COD, and reducing nitrogen and phosphorus. So as we move on, we are looking at this stage a lot closer, and we'll come on to why that is in a short while. Following secondary biological treatment, we move on to the tertiary treatment step. So further removal of nitrogen and phosphorus, and then using technologies such as UV ozone and chlorine disinfection, we're removing or stabilizing pathogenic microorganisms. And that's predominantly the last step in the works prior to discharge into the watercourse, whether that be a sea outfall or local watercourse. So I can just, sorry, just a quick one, just to move back. We see a couple of hands and questions. A question on the sand, sorry, on the sound. I guess anyone can everyone hear okay, or? Okay, perfect. I think we've got a few issues from our attendees are a little bit further away geographically, but we'll hopefully pick that up.
If there is a problem, it might help to reconnect the phone or computer.
So we obviously treat our wastewater and discharge it into watercourses generally, but we do have some elements of secondary waste from and production from those processes. So that's generally in the form of sludge. So we use sludge treatment, digesters, dewatering, thickening to minimise the amount of sludge that we are handling. So that's the amount of sludge that's either going to be treated or taken and disposed of, or even reused, and potentially in some cases returned back into the process. So as we already mentioned, we're going to focus today on the secondary biological treatment step. The main reason for that, as you can see here, is that out of the wastewater treatment cycle, around 62% of the energy used in the wastewater treatment step in the wastewater treatment plant is the aeration part. So that's made up of power to blowers to provide air into the aeration system. It's made up of power for things like mixers for use in anoxic and anaerobic zones. So as such a large portion of the energy usage, we feel that the aeration part is a good place to be optimizing process performance and gaining efficiencies to reduce the total overall power use for your plant. So if we just cover quickly before I hand to Magnus the various elements of secondary biological treatment. If we start from the front end of the plant, we have mixers, as we've already mentioned. So that's to provide a homogenized mix of the wastewater prior to treatment, so ensuring that all the solids remain in suspension or are resuspended, and that's in anoxic and anaerobic zones. We have aeration in the main zone, aerobic zone of the process, although we do in some scenarios use aeration as part of the anoxic mixing process in lieu of using mechanical mixers. We have the blowers, as I've already mentioned, so they're the big power user within the process. producing air to the diffused aeration system. We can also have ozone within the plant, and that's generally used for odor control or reducing and breaking down the sludge as it's produced. Quite often when we're within a process that requires denitrification, we do use small inline mixer pumps or other types of pumps to recirculate the mixed liquor back into the anoxic zone. So that gives us a small element of power, and then of course we've got the pumps that take any RAS and pump that away or back into the process as needed. We have already obviously mentioned some different types of process step within the secondary biological treatment process. Things like SBR, sequencing batch reactors that use a batch treatment process. Aeration lanes, so conventional activated sludge processes, and oxidation ditches are three of the main processes that we see in this arena. So I'll pass you over to Magnus, who's going to run through some of the steps really, and some of the different ways in which the efficiency can be reviewed, looked at, how processes and designs can be optimized in order to reduce power and maintain performance.
Okay. Okay. It's a bit slow on. Okay, so we're starting to look at the actual biological system, and very often we talk about the actual process, how to optimize process control and so on. But there's a lot to gain looking at the equipment and how they work together in wastewater or the biological system. There's a lot of gain on efficiency, and if there are new investments, there's a lot to gain on investment cost. If this is looked upon as a system. So this part of the presentation, I will go into some of those, what the potentials are and so on. Starting off with the same pie chart as Adam just showed, that the majority of a treatment plant, of course, aeration is the heaviest piece. And of course, blowers is the machine that draws most of the energy in this. So we see as blowers selecting the right technologies and optimization and so on, blowers can save up to 30%. There are cases that are of course higher than this. And of course, aeration, optimizing that in its design also has a great impact. Same thing with mixer technology selected and how that is adapted to the tank geometries and so on has an effect. And on top of that, there are controls and so on that help as well. And if you look on this as a system, because all these equipment interact with each other, there are possibilities to look at wire to water and more truthful view rather than looking on equipment separated from the actual design. So very often a blower is designed separately from the aeration design, and the mixer design is selected based on fixed parameters that are given, and so you don't get an optimized system. So that's what we're trying to highlight here. So doing this, we see that there's a good way to get risk minimization in a total design, we would get increased efficiency because we would look upon everything as a system, and since what I said, everything influences each other on equipment basis, and there's a lot to gain. Total cost of ownership, of course, goes down. Functional guarantees are possible for a whole system. It simplifies what happened there? It simplifies the responsibilities, and there's a simple interface for contract consultants and end users. It's kind of shifting myself. And of course, as I mentioned, there's a possibility for wire-to-water guarantees when you have a full design together. There we go. So the basic design, so to say, it's not new, but you can design a system with a cheap aeration system. It will do the job, or a more expensive system that also will do the job. So looking at efficiency just for the aeration is a good step to start with, and that happens quite a lot. But in reality, a system adding blowers design to this, it might be something in between here that is best CapEx and OpEx wise, since blower design affects the capital cost quite a lot in systems. So designing these together can gain a lot. This is a real example from a case where a consultant had designed and said, okay, they want a certain number of diffusers, given a certain flow, and the pressure, of course, is what it is when you put the air through diffusers. But in our view, we wanted to change and give an optimized solution based on blower and aeration optimization. So in this first case, we had to have 400 horsepower, actually, a total of 1,560 kilowatts. Quite many blowers, 6 pieces in total. It will cost around 1 million euros for that. An optimized system where we increase the number of diffusers to gain efficiency. We lowered the flow, of course, and the pressure also went down. And we can manage this with less blowers, smaller blowers, a lot lower power consumption, and also at the same time a lower cost, even though the aeration was a lot more expensive. The blower's impact on total the price was quite a lot. So this kind of shows that having this approach, allowing for optimization in the system, can save quite a lot. This is quite simple. So 23% in this case on the investment, and 55% of power savings due to this. And over time, that's a lot of money to be saved. And in our experience, it doesn't happen often that we get to do this type of optimization. We're stuck with a more fixed solution, and then the blowers come later just to meet air demand decided early in the process. So if we go into oxidation ditch, we're adding one parameter to the design, and that's the mixers that come in, creating the flow in the tank, the bulk flow in the tank, and it could be 10%, it could be more, but that's gaining even more savings looking at aeration blowers and mixing in this case, because they affect each other quite a lot. So this is a design example, what the impact could be on capital savings. So for example, if we were able to optimize the system only by 10%, we have about a 13% saving on cost by doing this. And of course, if we go up to 40% in this specific case, it's up to 27%. So you never know how much we can save beforehand on the design. It's depending on geometries and possibilities and so on. But it's in with this range that the potentials are by having this type of approach, which is quite a lot. Looking on the energy saving for the same size of plant, it's 100,000 people equivalent wastewater treatment plant. By doing a savings 10, 20, 30, 40%, we can go from 12 to 39% energy saving. So that's quite a lot as well. So optimizing reduces capital cost and increases efficiency. So this is showing the savings over 10 years, life cycle cost. There's a question here, elaborate on the effects of the aeration versus flow. I don't know what that question actually means. Flow of aeration, of air to aeration. Could you explain that a little bit better, and I'll try to answer later on that. So in this case, we're looking at 10 years and with no effect and 10% improvement. And then over 10 years, we have 254,000 euros in energy cost in this case, which is quite a lot, and worth considering in these type of designs. One other thing that we want to highlight is there is some trends on mixing with air on the market, and it's claimed to be efficient. It works, but in our view, it's not efficient. If you think about having a room full with balloons and letting them go, and that's supposed to create mixing, you need a lot of balloons, and compressed air actually costs more to produce than if you have mechanical mixers creating the mixing effect. So this curve is actually showing what the difference is. Just wanted to highlight this, that there could be a perception that it is a good way of mixing with bubbles. It's saving cost for mixers, but in reality, you're spending costs on operation. So the observation is it's more expensive upgrades if you're rebuilding a system to this, and the energy savings are not better. There are claims that they are. Process results are the same. Could mean bigger blowers than needed as a result. So also capital cost could be higher looking at that type of system.
I think, Magnus, just sorry to jump in there, it's probably worth at this point noting the importance of a good process design in terms of understanding the flow and load as well. We see a lot of data coming into us where flow and load is extrapolated for future unknown flows, but a guesstimate on the flow increase that could occur, which is very inaccurate. And also we tend to find a lot of scenarios where, as the design goes through different stages from initial flow and load, each step has a small allowance factor put on it to account for unknowns. And then when it reaches the aeration design or the final process design, those different factors and allowances have added up, which means that we are massively, the process design is massively oversized for what the flow actually is ever going to be. So in these scenarios, that does mean that aeration systems are being oversized, and as a result, that oversize does lead to the over aeration, which obviously is the point Magnus is making with the over aeration, is that when we over aerate, we're wasting money to essentially mix using diffusers rather than things like technologies like mixers. So that's a really important thing to be mindful of when completing process designs.
Yeah, of course, that is true, and it is often seen. One way of getting around this, of course, looking at what the actual loads will be and what the future's loads will be, and add that into the considerations in the design and so on. That increases efficiency and also meeting any future demands on aeration. So if you look at oxidation-rich opportunities, it is the key is actually the ability to optimize aeration and mixing in these type of tanks. It is complex. But it has a lot to gain doing it the right way. So just to show a case story where we have adapted the design and also added CFD analysis to find the correct solution and so on. Otherwise, we would rely on theoretical rules for mixing and what happens and aeration and efficiencies and so on. So for this project, it's from Bjegemark in Denmark, which is a quite nice case. This is the Google Earth view of the plant, and you see it's being built at this stage. But of course now it's running. So in the scope for this was actually blowers. We used the Sanitaire Turbomax blowers in this, sanitary aeration diffusers, and of course we used the new adaptive 4320 mixers, which enable us not to oversize mixing, and you can also opt mixing effect when they're installed, because they have built-in frequency converters inside the motor, so it's easy to control as well. And on top of that, there was a control system. And in this project, the evaluation of the project was 30% 15 years LCC evaluation, 30% on price, 30% of quality of solution, which is more an objective way of looking at suppliers and so on, and 10% was based on reference. We used CFD analysis conduct, and it showed that there is a big potential of savings of 25 to 30%, and it also helped us to move mixers in the right positions and so on, because we saw that there could be some issues with the mixers due to air plumes coming into the propellers in this design. So the results of after 3 months of operation, the energy cost was 145,000 kilowatt hours, and this extrapolated to 1 year because they had summer loads and winter loads and so on. So it doesn't have the same power consumption over a year, but compared to what we guaranteed, we guaranteed 950,000 kilowatt hours per year, but the result is a lot lower. So this is due to the design and optimization, and the geometry in this case was quite favorable. The results were quite nice. So in this case, there were actually 5 bidders. You see how they were evaluated here. And looking at the total price, you remember that we said we can optimize and lower the total price, total cost of the project, and also gain efficiency. So that's exactly what we did in this case. And this project was in Denmark, so they didn't have a lot of references and so on. But still, due to the high impact of cost and energy efficiency, of course, this solution had the best outcome. The CFD analysis was quite extensive. It looked at bulk flow, sedimentation risk, air entrainment risk in the mixers, evaluation, excessive turbulence, flocculation evaluation, and so on. So there were a lot of different type of CFD analysis made, and also, as I said, we saw that air plumes would come into the mixer. So you can see here that there are some going into the mixer here, and we moved them to get away from that. So that also reduces future problems with mixers. And that would not be captured with normal guidelines and so on. So this is purely due to a CFD analysis of the total system. So in this Bjegemark case, looking at where the costs were for the equipment and looking at the CFD analysis, it was only 1% of the total cost of the project, which is extremely low. But due to the CFD analysis, we could do as up to 30% savings, reduce problems in the future, and so on mixers. So it has a low cost in relation to the equipment, but it adds more value when it's possible to do the CFD analysis. One other thing, that when you do an optimization, and if there is a clean water test and so on, there are different standards, but we also know that the test standards are not up to date, and especially for oxidation ditches, they don't work very well, but they're used as they were working correctly. So that's a gamble when you do an optimized system, where you actually end up. So this kind of showing what the impact can be on existing standards in the oxidation ditch. So on ditches in particular, it's minus 25%. On preparation method with sulfite and so on, it's plus minus 3%. Temperature and sulfite, minus 15%, loss of cobalt. So there's a lot of impacts. TDS, what is being used. Liquid volume, there's a low percentage deviation, effective depth, and so on. So there is a new, there's work ongoing to capture these issues with the Aeration standard. And Xylem is deeply involved in capturing this since we have the know-how, and the estimation is that this will come next year sometimes, but it could take longer. But it's ongoing anyway, and that's good to know. So if you have any questions on this presentation, it's just showing the principles and potentials of savings. It's not going deeper into the actual theory behind the savings and why and so on. That's another type of presentation, but it's just highlighting the potentials and so on that can be gained by looking at looking at it as a system. Meeting process demands, whatever they could be. So, Adam, you will take over for now. For the next.
Yeah, sure. Shall we maybe just pause here for any questions, Magnus? I see we've got a few. although they seem to be generally on the sound. So there's just the one from Stephen Letitia at the minute, which is the question is the 63% dependent on the type of aeration? For instance, wouldn't an RBC used to aerate be much less? I don't know if you can.
I would say that depending on equipment you selected and how they're optimized and controlled, you have a big span on the results. The more efficient and equipment and so on, and controlling the process differently, of course it goes down. Does that answer the question?
Yes, it would appear so. Yeah. Then we have a couple of others. So we have one from Jacobus van Heerden, which is, can we elaborate on the effect of the aeration versus the flow? So I'm not, that's quite an open question. I don't know if Jacobus, if you could provide some more detail on your question, that would be really good if you could. Cheers. And then another question from Tom Williams asking, would you consider microbial activity monitors better than DO probes? For optimizing treatment.
We will cover this later a little bit.
Possibly. Let's see. Okay, so they seem to be our questions for now. So yeah, we'll carry on. So obviously Magnus has covered a piece about the design of the system, how we can optimize different products and technologies within a solution to increase efficiency and performance. We're going to move on now to the control part. So again, we see.
I received a question. I think it's privately to me. I don't know, but it asked about the mixing handbook, which there was a picture on there, and if it's available online. It's not available online. There are discussions on doing it. So we see Xylem as market leader on the theories and technologies around the mixers. But for now, it has to be asked for to the local Xylem office and so on to gain access to this what we call the mixing Bible.
Yeah, and I see we've got 57 attendees, so I'm not going to suggest we can send 57 of these out. But yeah, if you'd like to get in contact with us on those, whoever that question came from, Magnus, if people would like to get in contact on the handbook, I'm sure we can help you out with that.
Yeah. And there's also a question here on spontaneous duration or stew rate in the plant. I guess it's referring to the Danish project there. And to be honest, we don't have that information. It's nothing that we've heard about as an issue. But so I cannot answer that for this specific project.
Okay, so yeah, obviously we can design a system extremely well, and in terms of gaining efficiencies by both looking at individual components and then the way in which components react together, such as aeration and blowers, mixers and aeration. When we look at control, we see various different ways in which control can take place, and of a colleague of mine always gives a short saying that was given to him, which is essentially if you can measure something, you can understand it. If you can understand it, you can control it, and then if you can control it, you can improve it, which does go hand in hand. That wasn't from a wastewater expert. That was from a guy who looks at business improvement. But it works very well in terms of control of a wastewater treatment plant and individual processes. The visual here is really looking at how we can understand different loads and elements of wastewater coming onto a works, in this case ammonia, and really better control the process to give the output needed, but also to save money. So in this scenario, we see a fixed DO control, obviously a permit for the ammonia effluent going out, and really, as we see on the top graphic, we see elements where we're over treating and meeting process discharge consents, and we see an element where actually we're not treating enough ammonia, so we don't understand the ammonia coming on, so we're just plugging along for the fixed DO set point and not treating as much ammonia as we need to. So really, in this scenario, understanding our process and controlling it better gives us two things. It gives us the correct process output in terms of the amount of treatment we're producing, but also enables us to save money, because if we understand and can treat the correct amount, it gives us the ability to reduce our energy. So changing our DO set point accordingly in this example to treat the right amount of ammonia, and therefore providing the right amount of air. So how would we do that? In a conventional nitrifying plant, we would use ammonia probes, we would use dissolved oxygen probes and MLSS probes. So we would adjust the dissolved oxygen set point on the incoming flow and the incoming ammonia load, and then use a mid-process ammonia probe to give us the feedback in terms of how much we are treating, so we can do any trims that are needed. For denitrification, very similar, all based on incoming ammonia probes, but we would also look to use something like an ORP probe to just give us that further understanding of the process. Obviously, aeration and secondary biological treatment isn't the only area we can improve and gain efficiencies. In primary settlement, we can measure many different parameters: ammonia coming in, phosphates. In PSTs, we can measure sludge blanket, and we can optimize almost any of those processes by understanding how the process works, and then subsequently what flow and load is coming onto the works. So as an example, for the sludge blanket in the PST, that would enable us, by understanding our sludge blanket, that would enable us to optimize our desludging times and rates accordingly. For phosphate in the settled sewage, we could optimize what dosing we're doing for carbon for BIOP. As we've already talked about, in secondary treatment, we've got many different options. We can measure solids to optimize sludge age. It's a really, really good way of ensuring we're treating the right amount and achieving best process. We can measure ammonia. We can prevent septicity in the anoxic zone by using ORP sensors. And again, coupled with the ammonia probes, we can use things like dissolved oxygen monitors to optimize demand on blowers and reduce the energy within that element of the works. Moving through to tertiary treatment, again, we've got many different parameters that we're looking to measure. We've got parameters for the equipment coming, the flow coming onto the process, and of course, as that final effluent leaves the tertiary step, the final settlement tanks, UV, we need to make sure we're meeting the discharge consent. So that gives us all our compliance data and confidence that any treatment prior to discharge is doing what it should be doing. A couple of questions that and thoughts that we have within Xylem when we're looking at control. So, are we looking at continuous aeration? Are we using a different process, say a sequencing batch reactor, that will at times change our outlook on what to measure and how to measure it? Is the nitrogen load very variable? We obviously see some changes in nitrogen load coming onto the works, but is that very, very unstable in terms of how it comes on? Are we controlling the aeration based on DO measurement? And do we adjust that DO measurement or the required concentration automatically? In most cases, we still see very much a fixed DO set point and very little chance to optimize in that. So the capacity and drive to use things like ammonia control or variable DO control really does give a step above all the things that Magnus talked about earlier in terms of gaining small incremental and in some cases large incremental efficiency gains. And then finally, does the plant have difficulty in meeting consents for ammonia or nitrate? And when we look at that, is it a case of we're struggling to meet those consents because we don't understand what's coming in and subsequently can't control the plant? Or is it that we fully understand what's coming in, but we need to do some work on the plant to gain efficiencies and increased process treatment capacity in order to give the treatment requirements that are needed? And finally, what payback time is required for any investment? We certainly in the UK, we see anywhere between 3 and 5 years. That's reducing now. So we would certainly like to think that increasing the control parameters and method of control would get some pretty short payback times. On the control, we've got a short case story. So this is a plant sterno, which is works in Sweden. So in this scenario, this is a really good, I think so, a really good and interesting case story, which shows 65% energy saving, and that's actually, when you think about it, quite a substantial saving. When we take into account the things that Magnus talked about earlier, we're looking at in this scenario where we were changing an old aeration system and blower combination to efficient turbo blowers and high efficiency disc diffusers. We save around 57%, and we get then to the 65% really just by improving the way in which that efficient combination of aeration and blowers is controlled. We apply utmost open valve logic, and we use a much more suitable control with DO, dissolved oxygen. So when we talk about control, we have obviously very direct process control, things like installing probes and controlling things directly. We also look and are looking more and more currently at real-time control using digital algorithms and machine learning. So we have now capacity, such as the amount of data that is developed on sites to really push how the works is controlled, and that's not looking at one single process step. So that's not just taking the aeration part of the works, but looking at the full treatment works and how that can drive efficiency. So taking the primary settlement tanks, optimizing them, understanding how that can impact what happens in the secondary biological treatment step, and really using all the different elements of the works to get much better control, much better performance. In the scenario, in our experience, we use through our Blue X platform a sort of three stage approach. So obviously we must collect data, we must understand how the plant works, and that's extremely important. If you don't understand it, you can't control it and you can't optimize it. So it's important to gain data. It's important to gain as much data as possible on as much equipment and plant as possible. Once you have that data, it's then possible to start running models and scenarios of how plant may react in terms of the process, and also the energy used. And then once you understand how it works and you have that knowledge, it's possible to obviously optimize that. So that full scale optimization we feel is almost the next big step in terms of what customers are going to be looking for, how they're going to achieve in many ways what is a set of small steps, achieving some efficiency gains from different elements of plant to really go into a full digital optimization sort of process. And this is the kind of savings that we see through just in these two case stories. These are purely savings made by full process control rather than individual control and optimization of individual pieces of equipment. So this is as I see it, this is really this is a cherry on top of as in the Sterno solution, achieving 65% based on just that one process. This is the icing and the cherry, really. So this particular project, there was a lot of excess power consumption in the aeration lanes, and also that was coupled with a client that was struggling within their power constraints to produce enough capacity to treat their wastewater and maintain their legal effluent criteria and discharge consents. So by using that three-stage approach to understand the site, the works, the process, to take the data, and then to enable the use of that data to optimize, we were able to reduce energy by 26.3%, which was around a €330,000 per annum saving, and it gave the customer a much more controlled, a much more confident capacity to meet his process discharges. And similarly here, this is a wastewater pumping project, and again we had a situation where the pumps were essentially just running on fixed speed for a fixed time scale throughout the day, and it wasn't as efficient as we see. By introducing automatic pump control, we massively reduced the OPEX, and also actually gave that pumping station more capacity to take incoming flow. And actually that's I think our hour's up anyway,